Right. So this is what I have presented. I hope you shall be remembering this. What is a chromophore? The conjugated system in a molecule present is called a chromophore. It is not essential one molecule shall have only one chromophore. One molecule have more than one chromophore present in it. Let's see, I have exemplified. This has two chromophores which are identical in this molecule. So they shall show same absorbance because these are identical. But here, if you look at in this molecule, this is a different chromophore having four double bond in conjugation, and here five double bonds are in conjugation or five electron pairs are in conjugation. All right. So this is more conjugated than this one. All right. It shall show absorbance at a different value. It shall show absorbance at a different value. So we shall get two different absorbance for this molecule. All right. So this is what are called chromophores. Another terminology that we use in UV visible spectroscopy is called lambda max. What is a lambda max? I shall present this with a known UV visible spectrums just from Fleming's books. I hope all of you have the Asad share a copy of the whole book, which is very good. So it is the most updated seventh edition. So it is having further linkages and some problems also in that. So it is everybody should get that save in with and get it photocopy and bind it. That is a very fundamental book, shall help you in further future. So this is the lambda max is basically what lambda max stands for. Lambda means wavelength, max mean maximum. Look at here. Let's say we have one chromophore. I have presented this graph with respect to only one system. What system? I have presented this basically just for the presence of lambda max is for such molecule which have only one chromophore. Let's say this molecule have one chromophore, this molecule has one chromophore, and this is all of them has one chromophore, but it is not this one. It has two chromophores. So if we have a molecule which have one chromophore, we get a graph like this. It means the wavelength from 200 or higher, they are showing, all of them are showing absorbance because they are also involved in transition, but very low of them show absorbance. It is not an intense absorbance. You have come across IR spectrum. So we have an intense absorbance there. So we get an intense signal. But here signal is not always intense. This is like a curve like this, a parabolic curve like this one. It is not always a sharp signal. So what we call is, here we use the terminology, the wavelength where absorbance is maximum. You see, this is a point in this curve where if I draw a tangent to x-axis and y-axis both, if I am presenting this here, this is called absorbance value, which is from 0 to 1 maximum, because 1 means 100% absorbance, no zero transmittance. So 1 absorbance is, this is 1. And you can see the where it is the central point maximum height, this value is called absorbance, and this value along wavelength, what value is this? This is called lambda max. This is also wavelength, it is also wavelength, it is also showing absorbance, but it is not maximum absorbance. So that wavelength where a chromophore show maximum absorbance is called lambda max. This is the lambda max in fact. All right. So this is our UV visible spectrum. We are having values lambda of 200 or 200 is having higher energy. Shorter is the wavelength, higher shall be the energy value. This is higher and this is lower. And this along this axis of spectroscopic method involving transition in vibrational and rotational energy level means like microwave, IR, Raman spectroscopy, etc. We always take transmittance quantity coordinates along this transmittance. And normally we may have transmittance just 0 to 1, or we may show percent transmittance. So it is 0 to 100%. Just we are multiplying that with 100, nothing else. So we can show this absorbance, maximum absorbance can be 1, minimum can be 0. If it is 0, transmittance 100%. If absorbance is 1, mean transmittance is 0. And we avoid, we doesn't have one value normally, because it absorbs all radiation. This is not normally true. If any spectrum show absorbance greater than 1, it shows that it is more concentrated. We have to dilute this. Keeping in mind, the Lambert-Beer law is applicable to dilute solutions, which are micromolars. Micromolar solutions we can study with Lambert-Beer law. So if it is showing an absorbance greater than 1, keeping in mind it cannot be greater than 1. Why? Because greater than 1 means what? 101, 102% absorbance. It is not possible. If 100 radiations are coming, it absorbs 101 radiation. Practically, this is not possible. Lambda max cannot be having absorbance greater than 1. If it is greater than 1, you are supposed to dilute the solution. All right. So dilution than 1 for lambda max absorbance, then this Lambert-Beer law is applicable, and we can make use of expression absorbance is equal to epsilon CL. Otherwise, if it is greater than 1, we cannot apply this on such solutions. It is concentrated solution. So Lambert-Beer law is only applicable to dilute solution, which are normally micromolar solution, mean 10 to raise power minus 6 molar solutions we normally use. So it is only applicable to dilute solution, not to concentrated solution. This is a drawback of Lambert-Beer that we get from the practical value of graph, where absorbance is maximum. This is the maximum absorbance. So I have highlighted this wavelength, and on x-axis is called. This is characteristic for one chromosome. Characteristic for one chromosome. So it is not dependent upon concentration. This is not dependent upon any other factor. It is constant value. So lambda max is not variable. Mean we have a say 0.2, so they shall have a different lambda max? Not at all. It shall have the same lambda max in fact. All right. So this is something which is very important to understand. In some of the books, in Fleming's books, you shall see we are not having absorbance as this position. Why? They are having epsilon value here. Back to the relationship. Look at this. Absorbance is equal to epsilon CL. If I take epsilon, epsilon is equal to what? Absorbance over CL. L value is 1 centimeter, not centimeter width. So it is 1. Ignore this one. So what is epsilon? Epsilon is absorbance over concentration. If we divide the absorbance by concentration at epsilon value. So in Fleming's book, you shall see along this coordinate epsilon is presented. It doesn't mean this is a violation of spectroscopy. No, not at all. Because they have divided. Rather, we calculate the epsilon value for different. We are going to calculate same. Yes, sir. The epsilon value is basically originating from. Rather, we calculate, let's say we have absorbance this. So we divide, because we know the concentration of the solution. If we divide this absorbance by concentration, so what that shall be? That shall be epsilon value. So here, what they do, what in Fleming's book is being normally done, they are taking along this coordinate epsilon value, because concentration is same. When this solution is here, when it is showing an absorbance at this wavelength, its concentration is same. When it is here, it also have same concentration. It also at this position has same concentration. At any position in this graph, it has same concentration. So when concentration is same, absorbance is varying. You see, here absorbance is different. Here absorbance is increased. Absorbance is further increased. It is maximum here. So when absorbance is divided by concentration, so that shall give you epsilon value. So we can directly take epsilon value from graph. So what is done here? The instrument is doing, we feed the concentration. This is the concentration. Concentration is in mole per liter. So 10 to raise power minus 6 moles per liter. It is not normally. So we put the concentration in a program and then it calculate epsilon along there. So we directly come to know the epsilon value from the graph. This is a more advantageable to us. So we don't need to calculate this one. What absorbance is here, dividing that by the concentration. This is done for us by the instrument, in fact. So we can have epsilon value also along this, which is not the violation of the spectrum. Next, if I present this very quickly, this is very, very important in this case, electronic transitions. Let's say for one molecule to absorb in UV or visible region, there must be two double bonds in conjugation minimum. If you have only one double bond, that is called isolated double bond. Maybe carbon, 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 oxygen, carbon, nitrogen, or any heteroatom carbon. So in that case, that shall absorb in VUV region. No, but when we are talking about UV visible spectroscopy for UV, if two double bonds are in conjugation, then they can only absorb in UV region. If it is single the bond, it shall absorb in VUV region, 3 to 200 nanometer range, mean below 200, which is not a UV region. So which is VUV region. So there are two possibilities. Let's say we have one double bond carbon carbon which is connected with one carbonyl system. All right. So this is a simple four carbon, one carbon carbon double bond and one carbon oxygen double bond. No, there are two double bond. They are in conjugation. So it shall absorb in UV region, not in VUV region. Now look at here. This is also four carbon, very similar to this. One double bond, very similar to that. But here we have another carbon carbon double bond. If we have two carbon carbon double bond, one carbon carbon and one carbon oxygen double bond, so they are in fact having a both shall absorb in UV region, right? So let's see first if I have presented whenever double bond is forming, so sigma bonds are also forming. A sigma bond is formed here, right? So what is another bond? Look at here. We have a two double bonds in fact in this case. Let's say if I present these are the two pi bonds that I have presented here. Let's say if there is no double bond here, so what shall happen? This molecule have carbon oxygen single bond which we call sigma bond. So sigma bond when formed, it releases more energy. Sigma and sigma star molecular orbitals are formed. So these are the two molecular orbitals, sigma to sigma star, right? So which is this one. Let's say there is no double bond here. There is no double bond here. So this is presented for that. There is no double bond here. We have carbon oxygen double bonds, one bond. So sigma bond is formed. We have a carbon oxygen pi bond, which is this pi and pi star. You see, energy gap between sigma to sigma star is always higher than pi to pi star because this is less stable. If you are comparing the stability of pi and sigma bond is more stable than pi because it releases more energy. The energy gap between sigma star is always higher than pi to pi star. And in the center here, what is highest in energy is N. N is what? N is the non-bonding electron pair present on this oxygen. Look, here the oxygen have two non-bonding electron pair. So these are also electron pair. They are highest in energy. They are, so when sigma bond is formed, both electrons shall accommodate in sigma, no in sigma star. When two electrons are being formed, pi bond is formed, both electrons shall go to pi, no one shall go to pi star, but they are higher in energy, non-bonding electron pair. They are present in highest energy. So this is the one when there is no double bond here. I have presented this. This is a chromophore. This is another chromophore. But this molecular orbital I have presented for a molecule where you don't have a double bond here. We just have a pi and pi star bond, right? But now look at here. If we have two double bonds, let's say butadiene, 1,3-butadiene. So it is having a 4 molecular orbital, if you remember. So number of conjugated atoms. Here 4 atoms are conjugated, all of them are carbon. So 4 conjugated system is equal to number of molecular orbitals. It has psi1, psi2, psi3 and psi4. They are also represented with phi1, phi2, phi3, phi4. Phi or psi, both are right. So it is psi 1, psi 2, psi 3, psi 4. They are the, we cannot say they are two pi bonds. They are conjugated in fact. When they are conjugated, they shall form 4 molecular orbital. The number of molecular orbital is equal to number of conjugated atoms. There are 4 conjugating atoms here. So there shall be 4 molecular orbitals of equal energy gap. This is sigma bond form, sigma bond, which is here, two electrons accommodated in sigma. So 4 molecular orbital, 4 pi electrons are there. So 2 shall go to the lowest energy level, then 2 shall go to the further next energy level, 4 are accommodated. Psi 3, psi 4 and sigma star, they are empty. Now, if you remember, we use two terminologies, homo and lumo. Homo is the, you see, all these three are sigma, psi 1, psi 2. These three are occupied. This molecular orbital, this one, which is highest in energy and occupied, is called HOMO. This is called HOMO, highest occupied molecular orbital. Highest in energy, which is occupied, which is this one. Because if transition is taking place from this, it shall transit from one electron from here to there. 3 electron cannot be accommodated inside 2. Or if one electron is transiting from sigma, it shall go to phi 1. It cannot go to phi 3, which is empty, because it shall regulate, it shall violate the selection rule. So electron shall be transferred from where? HOMO to LUMO, because this is highest in energy and this is empty. So selection rule is applicable here. It can transit from here to there. So this is lowest in energy, unoccupied molecular orbital. So HOMO and LUMO are most important energy level in transition and inner transition coordination complexes or metal ions, as well as in this conjugated system. If we have 3 double bonds in conjugation, we shall have 6 atom in conjugation, we shall have 6 molecular orbital. 3 of them shall be occupied, then psi 3 shall be HOMO and psi 4 shall be LUMO. So what is the energy gap here between HOMO and LUMO? This is important. If this is lower, it shall absorb at higher wavelength. If it is higher, it shall absorb at lower wavelength. This is the key of this whole UV visible spectroscopy that we shall further study in next lecture. So